Hello and welcome back to set theory. In the last time we went over the axiom of union and we use it to define this and this. This is called the binary union of two sets, and this is called the arbitrary union of a set. And just as a refresher, this notation right here, this means the set of X such that X is in A or X is in B. Okay, that's this. And then what about this guy? Well, this is the set of X such that there exists at least some Y in A for which X is an element of Y. It's not totally obvious that these two sets exist. We had to use the axiom of union to prove it. Today we want to try to find set intersection, both the binary kind, the intersection of two sets, as well as the arbitrary kind with the big intersection symbol. So let's do it. Let's define this guy first because it's easier. So definition, we define the intersection of A and B to be the set of X for which X is an element of A and X is an element of B. Okay, and if we rewrite this little and here in the logical symbol for and is a wedge. And this is also a way you can remember which is which. Notice the intersection has a wedge and the union has a V for or. These symbols look very similar, don't they? Now you may be wondering, well, how do we know that this set even exists? Well, here's what we can do. We know that this set exists, the set of X in A such that X is in A and X is in B. You can make a set like this, the set of X in some set satisfying a certain property. We know that this exists by the axiom of separation, rather axiom schema of separation. If you don't know what that is, I made a video on it. But now here's the thing. If you're in A and you're in B, then you're automatically in A anyway. So writing X as an element of A here is actually a little bit overkill. So we can just scribble that out and get this. So this set must exist. So here's a little exercise. What's the intersection of these two sets? Okay, now here we're taking advantage of the fact that 0, 1, and 2 are all distinct, meaning they're not equal to each other. Okay, so well, the intersection of these two sets is just going to be the set of things which are both in 0, 1 and in 1, 2. Okay, this part we can rewrite as X equals 0 or X equals 1. And then this part we can rewrite as X equals 1 or X equals 2. Okay, now for this to be true, for X to be 0 or 1 and X to be 1 or 2, well, the only possibility is that X has to be 1. Okay, so this set has only one element, namely 1. So this is the set of X such that X equals 1, which is just the singleton 1. So you can think of set intersection as just overlap. Here's another example we can try. What's the intersection of these two sets? And let's do it quicker this time. Remember, intersection just means what elements are common to both. So zeros in both of them and 2's in both of them, but that's it, because 1's not common to both of them. So the intersection of these guys is just going to be 0, 2. Okay? So now I want to define arbitrary intersections. But before we do that, I want to review quickly what an arbitrary union is. So the arbitrary union of a set A is just the set of X for which there exists some Y in A for which X is an element of Y. So in other words, the arbitrary union of A is the set of things which belong to at least some member of A. Okay? So we're going to define the arbitrary intersection of A to be the set of X for which, for any Y in A, X is a member of Y, if the set exists. In other words, the arbitrary intersection of A is the set of things which belong to all members of A. Notice that the only difference in definition is that the union uses the existential quantifier, whereas the intersection uses the for all quantifier. But notice I said if the set exists, because spoiler alert, it's not always going to exist. The arbitrary union, we know that this always exists by the axiom of union. However, there is no axiom that tells us that this exists. If it does exist, it's something that we got to prove as a theorem. So here's an exercise for you. Does this guy exist as a set? And the answer to this is actually no, but here's why. For the contradiction, assume this guy does exist as a set. Okay, well, if it does exist as a set, then that means this guy has to exist as a set as well, because that's what we defined it to be, if it exists. But here's the thing, this part right here is always true. And why is it always true? Because this is saying for every y in the empty set, blah, 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 blah. That's automatically true because there's no counterexample that could make it false. So this is the set of all x for which true is true. So that means the set of all sets exists because this guy has to be the set of all sets, which is a contradiction. We know that there is no set of all sets. So therefore, this guy doesn't exist. Okay, now what about this exercise? If A is not the empty set, then does the intersection exist? We saw if A is the empty set, then it doesn't exist. But what about if it's not empty? And it turns out the answer to this question is yes, but it's not obvious. It's something we got to prove. So proof, assume that A is not empty. We want to show that this guy exists as a set, but what's that the same as? That's the same as saying that this guy exists as a set. How can we show that? Well, here's the thing. We know that this guy has to exist as a set by the axiom schema of separation. Recall that the axiom schema of separation ensures that anything that looks like this is a set. In this case, our S is big union of A, and our P of X is this proposition right here. All right, so we know that this guy exists, but how do we prove that this exists? Well, notice they look very similar. The only difference is that the one on the top doesn't have this part, right? So basically what you got to do is you got to show that whenever this part is true for some set X, then X has to be in big union of A anyway. That will show that this part is redundant and can be scribbled out. So to finish the proof, we want to show that whenever this is true for some X, then X has to be in union of A. So let X be a set for which this is true. We want to show that X has to be in big union of A. How do we do that? Well, to be in big union of A, what is big union of A? This is just the set of things which are members of at least some element of A. In other words, we want to show that there exists at least some y in A such that X is an element of Y. And so now here's the thing. Since we know that this is true, we can use this to prove this. Although here we do have to take advantage of the fact that A is non-empty. And so now here's the thing. Since we know that A is non-empty, because that was our assumption, and we know that X belongs to every member of A, that's what this means in quantifiers, then it follows that X has to belong to at least some member of A, right? Because if A has at least one member and X belongs to every member, then it has to belong to some member. And since it belongs to some member, then that means this is true. And so that finishes the proof. So to summarize our results, we see that the big intersection of A is defined if and only if A is not the empty set. If A is not the empty set, then this guy exists, and it equals the set of things which are members of all members of A. But big intersection of the empty set is not defined. Now here's a neat little theorem we can prove. For any set A, the arbitrary intersection of a singleton is just what's ever inside. Recall the exact same property holds for arbitrary unions as well, as we proved in last lecture. And spoiler alert, our proofs are going to be very similar. By the way, we don't have to worry about whether or not this is empty because we know it's not empty since it's a singleton. So So let's prove this. Since this guy is not empty, we know that this exists, and by definition, it equals the set of X such that for all Y in whatever this set is, namely the singleton containing A, we must have that X is an element of Y. Okay, but this part, saying Y is an element of the singleton A, is just the same as saying Y equals A. We can rewrite this as the set of X such that for all Y which are equal to A, X is an element of Y. Okay, but this part right here, this is just a fancy way of saying that X is an element of A, right? So we can rewrite this as the set of X such that X is a member of A. And the set of sets which are members of A is just A itself, obviously. So that proves this is the same as this. Here's another theorem that we can prove. The arbitrary intersection of this pair is just the same as the intersection of A and B. Recall last time we proved that for unions, a very similar law holds. So let's prove this. Of course, when dealing with arbitrary intersections, we have to take care that this isn't the empty set, otherwise it's not defined. However, in this case, since we have a pair, it has either one or two elements, but it can't have zero elements. So that means we know this guy is defined, and what is this equal to? Well, this is just the set of X for which, for all Y in whatever this set is, X is an element of Y, okay? But now we can simplify this, because if you say that Y is an element of this set, that's the same as saying that Y equals A or B. So what's this whole thing saying? This whole thing is saying that if Y equals A or Y equals B, then X has to be an element of Y. In other words, that's the same as saying that X has to be an element of A and X has to be an element of B. So if we simplify this part, well, then this is just the set of X such that X is an element of A and X is an element of B. And what is this guy? It's just A intersect B, because that's the definition. That proves it. So let's do a practice exercise. Let's find the arbitrary intersection of this set. It's a set that contains two elements, this guy and this guy. Well, there's two ways we can do this problem. Way number one is that we can use this theorem that we just proved in order to rewrite this as first guy intersects second guy. Okay, and so this means that what are the elements that are in both this set and this set? Well, we look at their overlap, and the only element that's common to both is 2. So therefore, this is just the singleton containing 2. Way number 2 is we got to ask, what are the things that are in all elements of this guy? Okay, well, this guy has 2 elements, this guy and this guy. So what things belong to all of these? Okay, and you can see 2 is the only element that belongs to everything. So therefore, it has to be the singleton 2. Now, here's a definition you'll see a lot. We say that two sets are disjoint if and only if their intersection is just the empty set. Another way to think of it is that A and B are disjoint if they have no elements in common. For example, these two sets are disjoint because they have no elements in common. Or another way you can think of it is that if you take the intersection of these two sets, well, it's the set of things which are in both, and since there's nothing in both, then that is just the empty set. But as another example, this set and this set are not disjoint from each other because they do have an element in common, namely 1. So we see if we take the intersection of these two guys, you get singleton 1, which is not equal to the empty set.